All right, guys, I'm picking right back up again. So we just talked about isotopes. Hydrogen has 3 isotopes. They had different masses, different numbers of neutrons. These 2 are stable isotopes. This one's radioactive. On the periodic table, though, periodic table can't give you all 3 masses of the hydrogen atoms. So instead of giving them all separately, if you look at the periodic table for hydrogen, the mass that's given is what's called a weighted average. Meaning if you have a container, like a balloon filled up with hydrogen atoms, and there'd be millions and millions of hydrogen atoms in there, actually like trillions or quadrillions of hydrogen atoms in a balloon of hydrogen. If you figure out what's the average weight of these 3, well, all 3 of them are not equally important. If you actually count, like looked at the atoms inside, and if you could actually like measure them, almost all the hydrogen atoms in a balloon would actually be like this one. Like 99.9% of all hydrogen atoms are hydrogen 1. And then like 0.1 or 0.01% of them are hydrogen 2. And then a tiny, tiny fraction are hydrogen 3. So if I'm going to represent the average of these 3, it makes sense that you're going to favor the one that's more common. Hydrogen 1 is much more common in a sample that has hydrogen in it. Almost all the atoms are going to be hydrogen 1. So we want the average that we report to favor the more common isotope. So that's what this is. The average weight of hydrogen favoring hydrogen 1 because it's the predominant isotope. Okay, so that happens for all elements. There's a way that we can calculate what the average atomic mass is going to be. So if I have bromine, it has 2 isotopes. It has bromine 81 and it has bromine 79. This is a weird one that it's actually about a 50-50 mix, okay? But if I want to calculate what's the average, if it's a 50-50 mix, I could actually just do a normal average, which is just add the 2 together and divide by 2. That would give me the average. But we're going to go through the exercise of calculating the weighted average the way we're supposed to. So here's the equation. It's going to be the weight of the first isotope, and usually we have the units are usually AMUs, atomic mass units. So it's going to be the weight of the first isotope times its percentage. The one trick here, the percentage needs to be in decimal form. So 50% is going to be 0.5. If it was 3%, that'd be 0.03. Okay, so just remember you divide by 100 or move the decimal over 2 places to change percentage into decimal form. So it'll be the first isotope's weight times its percentage in decimal form plus the second isotope's weight times its percentage. And then if we have more isotopes, you can add another term, the weight times the percentage. For as many isotopes as you have, you want to add them all together. Just make sure for this to work, you have to include all the isotopes, which means the percentages should add up to 100. Okay, so if I only have 2 isotopes, 50 plus 50, that's 100%. You have to account for the whole sample. Okay? So to do that, and here I'll do it on my board again. The calculation is going to be, let's call the first isotope that's mentioned in the problem is 81. 81 AMUs times 0.5 plus 79 AMUs times 0.5 also. And if you plug all that in, that's going to equal the weighted average, which if you do that, it's going to come out to be 80 AMUs. Okay, so that's how the weighted average is calculated. So, next problem. Here's a real element. It has 3 isotopes. Now the isotopes, something that's kind of important to know. On the previous slide, it said that bromine had an isotope that was 79 and an isotope that was 81. Those numbers are actually rounded. Okay, whenever you have an atom, when atoms form, if you take the masses of the protons, the mass of the neutrons, which are not actually equal to each other, but when the nucleus is formed, when the protons and neutrons come together, a little bit of the mass of the nucleus gets converted into energy, That's Einstein's equation, E equals mc squared. And that becomes like the nuclear binding energy that holds everything together. It's an extremely powerful force. But so the actual mass of an atom is not going to be a whole number. It's never going to be a whole number. Because number one, the protons and neutrons aren't really equal. And number two, when you put them together, a little bit of the mass gets turned into energy. So when I say bromine 79, the weight of bromine is actually not 79. It's either a little less or a little above the 79. Now, you'd think that it would always be a little bit less, but actually there's a reference. The only atom that's given a whole number weight is carbon 12. All the weights on the periodic table are determined based off of the isotope of carbon that weighs 12 AMUs. That one's 12.00000. Everything else is based off of ratios from that number. Okay? So, this one, I might call this isotope, if I knew which element it was, I'd say this is element X, 28, 29, and 30. I'll often just round it to the whole number, and sometimes we just use that number as the mass. But if we want to be more accurate, we want to use the best numbers available. So if we've actually measured the true masses, it's better to use those. Okay? So for there's 3 isotopes. For the first isotope, that is the mass. Here's its percentage. So if I want to do the equation, it'll be this mass times 0.9221. Remember, put it in decimal form. Plus the second isotope, it'll be this mass plus 0.0470 plus this mass times 0.0309. So it's always mass times percentage for each of the 3 and then add them all together. If you do that, go ahead and do it right now. I'm about to say the answer. The answer to that will be I think it's like 28.08 or something like that, 28.07, 28.08. So then if I look and say, okay, well, that's the average atomic mass of these 3 isotopes. If this is a real element, I should be able to look at the periodic table, which I have on the wall over there. I should be able to look at the table and find an element that has that average mass. And if you do that, it should end up being silicon. Silicon's mass on the periodic table is 28.08. It's the weighted average of these 3 isotopes. Now, if you didn't get the exact same answer as what's on the periodic table, we'll just realize these 2 numbers here only have 3 sig figs, and scientists who are actually developing the periodic table, they probably did this calculation with more sig figs at the end, so their numbers will be a little bit more accurate than yours, but you should be pretty close. All right, so then I have one more. I have an element europium. It has 2 isotopes. Now here's one that actually shows europium 151 has an actual mass of 150.9196. So it shows that the real mass is close to 151, but not the same. Okay? And then the other one, 153, is my isotope, has a mass of 152.9209. So I have 2 isotopes. I know their masses, and then it actually gives me the average is 151.96. So if you remember our equation, the average 151.96 AMUs, the weighted average equals the weight of the first isotope, which is 150.9196, times the percentage of isotope 1, plus the second isotope, which is 152.9209, times its percentage. Now, so when I set this up, again, this is kind of we got the chemistry part, but now we got to do some math. You got to remember algebra here. So I have the first percentage and the second percentage. A lot of students, if they had to solve this problem, because the question asks us what are the percentages of the 2 isotopes. There are 2 things I don't know. So a lot of students would want to say initially, well, the first percentage is X, and the second percentage is y. If you do that, you're done. Okay? You can't solve, if you only have one equation, we can't solve for two unknowns. So you have to realize the two percentages are dependent on each other. They're not independent variables. So if one of them is x, and let's just say that like one of them was 40%, we know the other one's going to be 60%. If one of them is 30%, the other one's got to be 70%, because it's always going to be the first percentage and then 100 minus that to get the second percentage. Okay? Well, here I can't do that because we're not doing percentage, we're doing the decimal form of the percentage. So instead of 100 minus x, we're going to do 1 minus x. So now we should be able to do the algebra. You know, you multiply these, you got to multiply that in and that times the 1 and that times the x, and then do all the solving. But you should be able to solve for what x is. X will be the percentage of that isotope. And then once you have it, then you can do 1 minus that to get the percentage of this isotope. I'm going to leave that for you to do. Hopefully you can figure that out. And that is the end of the first chapter 2 PowerPoint. Next video, we'll start the next